Hi, this is Shelley Physics, episode on Amperes Law. So recently, we've been looking at magnetic field around current carrying elements and such, and applying the Biot-Savart law. If there's a current I passing through a conductor, and then it would have a magnetic field mu naught I over 2 pi r. And this would be close to that conductor if it's a long conductor. So here I have a conductor with a current I coming out of the page. We're looking at it head on. So what kind of magnetic field would it have around it, or what would that look like? Using the right hand rule, the current coming out of the page, the magnetic field would curl around it in this kind of circle. Okay. So over here the magnetic field would be up. Here the magnetic field would be to the left. Over here down, and here it would be to the right. So these are all the magnetic fields. Okay. Well, you'll notice that at each of these points, they would all, as long as they have a consistent radius distance r, they would all have the same magnitude of the magnetic field. So if we rewrite this, we'd have a 2 pi r equals mu naught I. Okay. So if you look at this format here, the magnetic field being constant or the same all the way throughout that line, and that line makes a path 2 pi r. That's the circumference of this imaginary circle around it where the magnetic field is constant and the same. And what we've done is multiplied a magnetic field times a circumference. That's the length around. And that gives us the constant mu naught, magnetic constant, times the current through that wire. So I guess Ampere would look at this and saying, okay, can I apply this to other systems? What if we have 2 wires or 3 wires, and what if the current's going this way and the other current's going that way? And maybe ask, what about the magnetic field within a wire? Have you considered that? So if we look at this expression and realize that this 2 pi r is the sum of a loop. Okay, so that this is the length, and if we sum up the length of that entire loop, there's a little slice of that loop dl, and if we sum them all up in that closed circle there, then it's the same as closed integral of b dl. Now is this b and this l are both vectors. So if we look at the little length dl, as I go around the circle this way, the dl is in the same direction as the magnetic field at this point, and a little segment dl is in the same direction as the magnetic field at that point. So you'll see that this is the dot product, or the scalar product of b dl. Now it'd be equal to mu naught times the I, the current that's enclosed in that plane. Okay, and what we have here, this is called Ampere's law. Now it doesn't just work for a single current element. It'll work for some other systems that we're going to look at as we go through this segment. But this is Ampere's law, and it's really important to note here that this current enclosed would be any current elements enclosed, and it's this nice two-dimensional plane also that we're looking at here. Just the current enclosed through this segment of the long wire. Now, if you look at this expression, does it remind you of anything? Does it remind you of something involving an electric field in a closed surface area? Do you remember that charge enclosed over epsilon naught? This was Gauss's law. So if you recall what Gauss's law did for us and how it simplified a lot of very common situations where you're at first calculating these electric fields that were very complicated to get through. And likewise, using the Biot-Savart law, some of those magnetic field calculations were equally difficult to move through. We had to use a trig substitution and an integral, and it just took pages and pages of derivation to get through. Gauss's law simplified that process for electric fields quite a bit. Ampere's law does the same. So this is our friend, this is our shortcut. And don't let this kind of thing bother you. It's usually some kind of path where we can add up segments or add up the little small pieces of dl to make a circumference, 2 pi r. So this is generally what's going to be happening here with Ampere's law. So what do we know about, I'm going to blow this up a little bit. So this is the same conductor with a current coming out of the page. If we plot magnetic field versus R, okay, versus distance, then out here at the radius of that conductor, big R, we know that B equals mu naught I over 2 pi R. So you'll notice that this is an inverse dependence, 1 over R. So we're going to have some kind of plot that looks like this outside of that radius. It's a 1 over R kind of graph. If this continued inside, it would go up to an infinite amount. So the big question is, what is going on inside here? What does the graph look like inside of this? Our first application of Ampere's law is to look inside of that wire. Inside of a wire, I'm going to look at a wire kind of along the side now. Take a little slice out of that. Okay. So inside that wire, instead of looking at, let's say, the big R on the outside, what if we're looking at a tiny slice of that slice, a piece of that? Okay, take out the middle of the pepperoni. And this little r is what we're looking for here. If you think about current or charge passing through this wire as it flows in a current, only some of that charge will move through this smaller slice, while other parts of the charge will move outside of that. So we apply Ampere's law. So when we look at the inside of this little loop, this closed integral of b dot dl will be a b times, and we sum up all that length, it's going to be a 2 pi little r. Now keep in mind here, big R is the size of the entire, the radius of the entire conductor. Little r in this case is the radius of the inner part, this portion we're looking at. So what is the magnetic field at a small point inside of this conductor? So for that, the entire current is not flowing through this little piece that we're looking at. Only a portion of it is. So if we take a moment and recall, this is just one way to do this part. In general, current is in little q, the charge, Vd, times the area. Okay, so if you recall the definition of current, given the drift velocity of charge moving through a conductor that has a charge per unit volume in, or the number of charges per unit volume in, and a cross-sectional area A, right? So if we look at the total enclosed I, this would be the A of our enclosed amount, okay? And we can also compare that to the total current, if there is a current I passing through this little segment, the whole total current I is that, where, okay, if you consider that inner shape there, the I enclosed would be just the charges that are moving through this little tiny slice, but having just an inner portion of that wire. So we'd still have, this N is still a ratio. It's number of charges per unit volume. Q would be the elementary charge of electrons. The drift velocity should be the same. But the only thing that's different is this A. This would be the total area of that larger slice compared to the smaller. So if we compare that and make a little ratio, I enclosed over I total equals the enclosed A over the total A. You'll notice all these are the same. It would cancel out. And what we're left with is let me rewrite that, I enclosed over I total would be A enclosed over A total. Now what is the area of a little slice of pepperoni? It's pi r squared. Now I've got to be careful, the enclosed r would be little r, and the total, the r for the total area would be big R. All right, so we have a ratio here. Pi's cancel, and I get the I enclosed. If we solve for it now, multiply by I total is little r squared divided by big R squared times that I total, the current passing through the entire conductor segment. All right, so I have my ammunition here. We're going to plug this in right up here. I'll go ahead and do this in a separate sheet of paper. So moving it up, we have B times 2 pi little r. It's going to be important in a moment. Equals mu naught. And we're plugging in this little creature here. R squared over big R squared times, now just instead of I total, I'm just going to define this as I instead of the enclosed I. This is generally when we say there's a current through a wire, it's called I. So that's the total current through the wire right there. Okay. And now we have a little bit of moving around to do. We've got a B. What is the magnetic field at that point R? So I could also call this B of R, right? Mu naught over 2 pi. That 2 pi will drop down here. Now notice we'll have an R on each side. Okay, so one of those R's will cancel, and I get an I up here, and then a little r over a big R squared. Okay, just to rewrite that, we have a B of R function here. Magnetic field is a function of R. So mu naught I over 2 pi big R squared. Now all those are constants. Then we get left with R out here. So what kind of function is this? This is linear. And the slope is mu naught I over 2 pi R, 2 pi R squared. So we back it up here. What does what's the function look like where R, little r, is less than big R? It's a line, right? So if we look at the limits here, at R equals 0, the magnetic field is 0. And at R equals big R, what's the magnetic field there? Oh, that would be mu naught I divided by 2 pi big R divided by R squared is just a single big R. Okay. So now we get we'll redraw our graph. This is our current element, radius big R, magnetic field as a function of R, and we'd have the outside function. Now keep in mind this is mu naught I over 2 pi R. But right here at this point, R is equal to big R. So at this point, this is mu naught I over 2 pi big R, right at that point, whatever that value is. And that's where both of the graphs will meet up. We're going to have, on the inside, a line starting at 0 and reaching up to pi, mu naught I over 2 pi R. So there's going to be a straight line increasing there. We're looking at the magnetic field inside of a wire, something we could never really measure with an instrument. So that's one application of Ampere's law, magnetic field inside of a wire. I'm going to do one more major application here of Ampere's law, and that's inside of a solenoid. Okay. All right. So I don't know if you recall a solenoid, but a solenoid is basically a bunch of loops, all the same radius. And inside of a solenoid, there's a nice constant magnetic field produced by those coils of wire. All right. So as we send a current up like this through that solenoid, and at each point in the wire, there's going to be a magnetic field. Whether it's in the bottom, it's going this way, the current's coming out of the page. At the very bottom of the coil, so there's a magnetic field to the left. Or at the top of the coil, the current will be going into the page, so there's also a left-hand magnetic field there. So it's a nice constant magnetic field in the inside. While there are trace magnetic fields on the outside, when you get just a little bit further away on the outside, the magnetic field is just about zero. It's very weak. So we mainly focus in solenoids on the inside of that solenoid. Every single segment of this solenoid wire is contributing to magnetic field on the outside, but on the inside. But on the outside, it just kind of disperses out into space. It's very weak. So here, what I'm going to do is something that's very difficult for me. I'm going to try to graphically just draw these segments of the solenoid. Just take a small piece of this so that we're looking at these cross sections of the wire in the solenoid. Okay, I'll just do this. Look at that, I screwed it up. Woohoo! I'm doing some kind of weird impressionist art here, evidently. There we go. Told you I'd probably screw that on up. Okay. So here, if the current's flowing out of the bottom, coming up towards us, out of the page there, going into the page at the top, we have several coils of this solenoid. All right, so here I is going in, and down here I is coming out. So just broken up the coils of this solenoid. All right, now we're going to write down Ampere's law. See what the heck we can do with this creature. I enclosed, current elements enclosed. All right, so what does the magnetic field look like inside of this solenoid? This is what we can determine, hopefully. All right, so to do this one, what we're going to do is select a path that can be determined. We need to sum up magnetic field along path segments. Now keep in mind, this path doesn't have to always be a circle. All right, it can be a square also. Nice thing about a square is we can tell the distance or length of edges of this square or rectangle. I'm actually going to use a rectangle in this case. Keep in mind all along our magnetic field is going to the left through there. All right, so my segment here, I'm going to take my loop. And also keep in mind that these coils continue going out to the left and coils continue out going to the right. There are always fringe effects to things like solenoids, but right in the center, the main component of the center of the solenoids, they're always going to have a nice consistent magnetic field. So here's an actual solenoid. It's got an empty spot in the middle. So mainly in the middle area, right through here, it's going to be a nice consistent magnetic field, even up to this point. Sometimes you'll start seeing fringe effects out here or over here along the fringe, but right in the middle, these nice constant magnetic fields produced. So what is the value of that magnetic field if we've got a current I passing through the pieces of the wires in the solenoid? That's what we're looking at here. So my path, I'm going to take a path this way, and then up, and then over to continue the loop and down. So it makes something like a square or a rectangle. I'll call this a square, all of length L on each side. Okay, and we got I. So I think that is about it. That's all we're going to need there. We might need a few properties of the solenoid itself. I guess we would need this. We would need probably the number of turns per unit length. Okay, so I'll call that something similar or familiar. I'll call it little n. So little n for when we're looking at drift velocity and current. Little n was the number of charges per unit volume. So this is also kind of like a number of per unit something. So little n is often used for that, number of turns per unit length here. All right, so let's apply Ampere's law. We're going to have 4 different segments here. So I'm actually going to sum up 4 different B times DLs, or B dot DLs. We do have to remember that. Okay. So the first one I'm going to start with is, I'm going to just start at the top here. Out here on the top, the magnetic field is essentially 0. It's very, very weak outside of a solenoid. So for that first B dot DL, we're going to have an L times 0 along the top as we go along that loop. All right. So there's 0 contribution to this sum of B dot DL. And if there's a magnetic field out here, it would be in the same direction or similar, but it doesn't matter because the magnitude of the magnetic field is 0. Now as I go down, okay, I might have whatever that magnetic field strength is over here on that, we'll call that the right side, okay, times the length. It's hard to tell what that's going to be, but there's a really important fact here which negates any considerations of what the heck this magnetic field contribution might be. And that fact is that this DL, this length, if we sum up all these little DLs along this length, they're in the downward direction. And the magnetic field right above this wire is either to the left or the right. So actually, if it's going in, the magnetic field right above this, see how this current is going in right there? So the magnetic field doing that current element is to the right. It's perpendicular to L, to DL. So B dot DL is like A dot B. So A dot B is AB cosine theta. B dot DL is BL cosine of the angle between L and B. So since B up here is going to the right and DL is down, that angle is 90 degrees. And the wonderful mystical magical thing about cosine of 90 degrees is it's 0. So there's 0 contribution to whatever that magnetic field would be. Then, next part of our loop, we're on the inside now. On the inside, okay, our DL path is along the same direction as the magnetic field. So that is the constant magnetic field we're looking for, the B of that bottom piece. And the length is L also. Here the direction, the angle between B and L is 0 degrees, cosine of 0. And then we finally get to that left segment, and for the same reasons as the right, the left segment is length L, but the angle between them is 90 degrees. And all that equals I enclosed times mu naught. I wrote that backwards, so I'll fix that in a moment. But the nice thing here is these 3 components cancel. And cosine of 0 is 1. So we're left with BL equals mu naught I enclosed. All right. So our last piece of this little puzzle here is what is the I enclosed? Well, if I have 4 segments and there's 4 turns per this unit length L, then the I enclosed would be just those number of coils times the current through each one. They have the same current flowing through each coil. All right, so we're going to have a mu naught times I through the solenoid wire times N. All right, so finally, what do we get out of that? If we divide L out of both sides, we get the magnetic field being mu naught I times N, the number of turns, divided by L, which is the same ratio of little n, the number of turns per unit length. So that would be for a solenoid. Okay. You usually don't count up all the turns in a solenoid. Obviously, that would be kind of difficult there. Okay, I'm going to count those up. Be my guest. But if we just look at the manufacturing specs of this thing, sometimes these are, actually this one is coiled like over top of itself many times. So that would be very difficult to count. So instead, we'll look at the specs on this and get the number of turns per unit length. Or we could take, the length of the wire and figure out the length of the whole thing, so we could figure out the number of turns. There's a lot of different ways to work that out. But this is the in number of turns per unit length that involves the L, that includes that big L there. So the last thing I want to do is revisit this DL character. In the first example of the inside of the wire, this DL was a little loop inside of the wire. This is an imaginary loop. It's like with Gaussian surfaces, they are imaginary surfaces we were putting around the object. So this DL is not the kind of DL we've been looking at in like the Biot-Savart law, like IDL. This L was a length of current, a current length, IDL. But this the loop we're looking at here, this little DL is separate from the current element. This is the magnetic field around a loop, around a pathway. It doesn't have to be a circular loop. It could be a pathway like we looked at with the solenoid. This was our loop here. It was an imaginary pathway. So it doesn't physically have to be a wire that goes around it. It doesn't have to be an actual object that is traversing that path there. What we mainly look for is at least a segment of that pathway where the magnetic field is constant or consistent. In our first example, the magnetic field at any point at a distance little r from the center of this conductor was the same. So you'll notice the similarities between Gauss's law and Amperes law. I hope this episode was helpful.